and it's my pleasure to be your moderator here today, welcoming you with a few partner organizations. So we organize this together with the Alliance for IoT Innovation, Artemisia, EU-IoT, and the European Commission, and you will hear more about the context in a moment. Just some housekeeping rules. The session is being recorded, so you have to leave if that's not working for you. It will be published also later together with the slides and so on. So you don't have to ask for that. Please mute and close your video when you are not speaking, and feel free to use the chat. These sessions are meant to be really interactive. So we are in listening mode, of course, giving some context for what we're listening for, but please use the chat, and you can raise your hand as well, and please reach out to the info at NGIoT if there's any issues technically or so on that you experience. The link is also on the event web page, so if you somehow need to something, you can find it there. This is the program for today. We will have some strategic overall views relating to industrial IoT, and dive a little more into edge nodes and the use cases around these. I'm sure many of you are familiar with the concept, but what is it actually in the roadmaps that we are putting up? Then we have some more open parts with brief statements from around the stakeholders, and we wrap up and look a bit forward for the coming sessions. So I give you a very short introduction to IoT, then I give the floor to Rolf Remenstein, head of IoT for European Commission, Sandro Delia, also from DG Connect, but on the digital transformation of industrial ecosystems. So welcome here. So NGIoT, Next Generation Internet of Things, is an effort set up by the European Commission and operated coordinated by myself and with colleagues, where we are supporting with input for the upcoming roadmap for IoT research, innovation, deployment for Europe. And as you can see on the screen here, so by May, we will deliver sort of the conclusions from the consultations and the stakeholder engagements that we have been conducting, and turn that into a final roadmap. The roadmap already exists actually in a preliminary version, but will of course be targeted towards the now very soon to be opened Horizon Europe, Digital Europe program, etc. policies. So of course, IoT and edge computing is essential for our globalized digital economies. But what is it then? How do we bring that into support in priorities? Not going to go into that, of course, that's self-explanatory. Just a little bit on landscaping. So of course, IoT and edge computing, I mean, that's basically anything you could say which is not the centralized part of the computing continuum, but is on the edges. So obviously, it is a very diverse stakeholder landscape. Just to say that, of course, that is the basis from which we start. This workshop is the third in a series, well, more if you count the more cross-cutting ones, and upcoming ones are also in the program. So please look forward to the energy session and the health and care session on the 18th of May, and you can already now sign up on the NGIoT website. Perhaps we can put the links to those sessions in the chat as well. And what we are doing is that we are, of course, looking to what are the trends in the market, what are the priorities from the stakeholders, and how do they form technology roadmaps, not just generalized technology roadmap, but really specifically on the IoT domain, of course, with all the complexities that kind of scoping entails. And voila, here we are today looking at manufacturing. So previously we've been looking more about on the cross-cutting horizontal societal perspectives. So with smart cities and communities, rural communities, Agrifood, which is very, very complex value networks. Now we turn the focus to the manufacturing. So with that introduction, I give you the floor. Rolf, please share your vision with us, and I'll just unshare my screen so you have the floor here. Thank you.
All right, thank you, Martin. I'm sharing my screen again. Should come in a second. All right, you should see it now.
We see it well, thank you.
Good. Good afternoon, everyone, ladies and gentlemen. Thanks for joining the seminar. I work in DG Connect in the unit Internet of Things, and I'm happy also that a colleague of mine, Sandro Delia, also from DG Connect, from a digitization unit, will join us today. Actually, IoT platforms in particular and industry, we were under the same umbrella and the digitizing European industry in Horizon Europe. And now I think we're going for new directions, and I think you will be curious to hear now, what are these about. So actually, the same umbrella is also the communication from the Commission on the Digital Decade, a compass and common targets until 2030. You see 4 directions: the skills, public services. You know that there's a lot of emphasis put at the moment into investment into infrastructure, connectivity, modernization of the infrastructure, 5G networks everywhere, boosting manufacturing and production of semiconductors. We're going to propose an IPC on microelectronics, encouraging more investment into cloud and data infrastructure, in particular, the target of 10,000 climate neutral, highly secure edge nodes, so it's quite relevant, and investment into research, innovation, and computing, so high performance computing, as well as first computers with quantum acceleration. Very relevant today is the business perspective. At the moment, many of the particular mid-sized companies and small companies are very cloud skeptic. There's a target to bring them to the cloud, focusing on innovators, in particular SMEs, to participate in the digital innovation. Actually, what do we see now as paradigm shift or trend? Famous industrial IoT platforms like MindSphere from Siemens, they have been ported to Amazon Web Services. Others like Predix, they got burst. There's a bit of a change in reorientation. Now we see a trend that there's still exponential growth of data, particular data from industrial systems on the shop floor, instruments, equipment, data driven through developments, industrial IoT, cyber physical systems, which are connecting local automation islands. Still, central cloud storage would not be prepared to cover all the data which will be produced in the future. It would have a raising energy profile, which would make sense, and would put incredible demands for transport networks. So there's to avoid the data deluge in the central processing, we need more computation close to where the data is generated. That would allow real-time and safety applications for deterministic and highly reliable automation and control. It will reduce dramatically the attack surface, improving security and privacy. It will be more energy efficient, reducing carbon footprint, and it will allow data aggregation and analytics along the computing continuum from cloud to edge to the operational and control devices. So what we see is that in the next 5 years, when industrial data is growing, there will be more processing. At the edge, about 80% is processed. We're looking for a decentralized approach with distributed and embedded intelligence, but also more communication and connectivity, allowing campus 5G networks for mobile automation, autonomous grounded vehicles, and integrated logistics, for instance. So this picture visualizes, the shift from cloud to edge to IoT. We see sort of a repartition of services and data processing. What we need is a federation of the resources. We have more distributed computing at the device level, at the smart device level. We have close to real time and device management at the edge level. And we still need the cloud, the orchestration with the cloud related to machine learning and artificial intelligence. Looking at a 5 years innovation perspective from our unit point of view and from the direct point of view, we need incorporating more power on the IoT and in the devices, building on advances in microelectronics, microsystems, and system integration. We will see that through new chip architectures, intelligence will be embedded at the device level. And we see that this real-time processing and low latency implementation of systems will drive the convergence of IoT and cyber-physical systems. So actually, why are we doing that? It builds particularly on European strength in building systems, in system engineering, in sensors, in actuators, and embedded systems. These systems will be enhanced through cloud services, which are largely general purpose, and at the same time, edge and far edge computing has to exploit future cloud innovation and services, but at the same time, and they have to be strongly customized towards the application. That is one of the strengths where European companies are located. So there's new opportunities for European industry to participate in this new data economy with a strong focus on system integration, system aspects at the edge level. So we're looking for a next generation of IoT and edge computing vision with a strong focus on system integration, lifecycle management, and building the next generation of industrial platforms and ecosystems. So way in a nutshell, I put on the slide a few messages. What we had a fireside chat, which was some renowned experts in a private meeting. The report is published. Again, we urge, a European strategy to seize these opportunities to bring together the IT and the OT world. They see edge computing as a game changer in the data economy, away from the leading cloud providers we have at the moment, and they call for partnerships. They build on partnerships with the leading hyperscalers, which are a fact today, but they call for a European level playing field with a strong link and foot in the edge domain. So actually, it's not only about technology. In order to build trusted and open vendor systems, we need B2B platforms for industrial and business IoT. And we need open interfaces and standards for interoperability, for data, for communications. We need the technologies anchored in Europe. And we have the challenge in order to build an ecosystem around that, new platforms, technology platforms, to include SMEs, innovators, new services to cooperate with large companies in today's very still fragmented industrial environments, very complex environments, into that ecosystem. So this, in order to realize, I think we need to talk about use cases. What are the key use cases underpinning these trends? And today, I think we have a strong focus on manufacturing. Taxonomy for the manufacturing edge. You see the picture over here. There are 4 pillars actually. One is the enterprise edge, with a strong focus on integrating IT systems with OT processes and operations. We see new possibilities through 5G networks, the mobile edge computing environment and standards being developed at the moment. We see new capabilities for edge devices, for distributed intelligence, but also for embedding AI. And the 4th level is we need sort of a new way of orchestration between the device layer and the cloud layer, where we call for a new meta operating system, what we call a new software framework at the edge close to the devices. very briefly, there will be opportunities to support that trends under Horizon Europe in Cluster 4, Destination 3. We call for a European platform for the edge in order to improve end-to-end response time, optimize operations of IoT systems and services, as mentioned, a meta operating system for the edge, reduce energy consumption, and allow this orchestration across devices, the edge, and towards cloud services. The work program hasn't been published officially at the moment. We're still waiting for the official launch, but you find pre-publications, leaked, unofficial leaked versions in the net. And I'm sure there are other opportunities, particularly domain-driven in the manufacturing, where Sandro then will give you a bit of a hint. Thanks so much for your attention, and happy to answer any of the questions. Thank you.
Thank you so much, Rolf, for this comprehensive overview, and also to the links. And again, we will, of course, share them after this session here. And also, I mean, if you want, you can put some of them in here. Sandro, from your side, from the more specific focus on the broader ecosystems around digitizing European industry, some reflections from your side on this particular focus now on edge, far edge IoT. Your floor is yours.
Yes, thank you very much. I hope I'm not muted. No, I'm not muted. So I'm Sandro Delia. I work for a unit in DG Connect, which is called the Digital Transformation of Industrial Ecosystem. What we do is basically two things. We work on the network of European digital innovation hubs that we are trying to set up with the Digital Europe program. And we work on the Made in Europe partnership together with the other DG, RTD, and the external partners on something which may be relevant for manufacturing and edge computing. I would like to start from the very top. If you think what's happening now, simplifying very much, because of course a slide is a bit simpler than the reality. The Europe or the world now is faced with the climate crisis, with the pandemic, which is not over yet, with a lot of global tensions, like maybe any time in history. But now the geography is shifting, especially with regards to China. And what is Europe doing? How is Europe answering to the global challenges that we are facing now? Basically, one big thing is the twin transition, where twin means green and digital transition. So this has been since the beginning of the activity of the new of this European Commission, has been at the core of the growth strategy and the general policy of the Europe. Then pandemic came, and we did the Next Generation EU or Recovery Fund, which is, let's say, the support, the very big financial support for Europe to create a digital decade, to make sure that digital technologies can be really at the heart, at the core of all the economic processes. Last but not least, there is the so-called open strategic autonomy. What does it mean, open strategic autonomy? It means making sure that while Europe is committed to open markets, to open free trade in general, we should make sure that we keep the strategic capabilities of doing very important objects or services which we need, we keep them in Europe, because we noticed that with the pandemic crisis that from one day to the other, it was not possible to find a face mask, which is something very simple and very cheap, but which is not done in Europe. It's done somewhere else. Now we are seeing at a different level that, for example, the automotive industry in Europe has a problem with the shortage of computer chips, because computer chips are manufactured not in Europe mostly. And this is a problem. It's a clear problem. I tell you that there is a lot more support and general political agreement on the twin transition and on Next Generation EU that on the concept of open strategic autonomy, which I see discussed in many cases. But nevertheless, the basic idea is that Europe should not be naive in pushing for open markets, and should make sure that we don't find ourselves in the next crisis in a big problem, big trouble, because we do not master anymore the technologies which are needed for a modern economy. Okay, what is important now from a technical point of view? I started working on the so-called digitization of European industry in 2016, which is now 5 years ago. At the time, I remember that anytime we did a presentation or a speech, we had to start saying why digital transformation is needed, why digitization is needed in industry. Now it's not the case anymore. Everybody understands it. And the reason is simply that digital technology is everywhere. If you think about any object which is a bit complex and that you use in your life, from the elevator to the car to the plane, and then any object which is used in a factory, from the automated conveyor to the numeric control machine and so on, all these things have a computer inside. So we have the perfect storm, in the sense that on one side, we have industrial processes which need radical changes to become sustainable. So we cannot go on in the 21st century trying to reduce emission of CO2 without changing radically the industrial processes which are at the basis of our economy. It will not work. We cannot go back in time. We cannot go back in living like in the Middle Age. And even if we would do so, I mean, it will not work anymore, because now there are 8 billion people on this planet. So we simply need to change radically many technologies and make them sustainable. And here, digital technology can help a lot, to improve processes, to improve products and services, especially to design new processes, which can make sense only if you have a digital technology behind it. Think about, for example, a very stupid, well, not stupid, but I mean, a very trivial example, garbage collection. Everybody of us spends a lot of time, sorting garbage at home. Sometimes I feel very stupid when I open a letter, paper letter, which has the plastic, window. I take out the plastic window and put in one place, and take the paper and put in another place. How much does this impact on the world? It's clear that there are things which do not make sense if you do them manually. Processes like cutting the paper from the plastic is something that has to be done automatically, and only digital technology now, with artificial intelligence, robotics, and so on, can help. So this is a very strong push for the so-called twin transition. Twin means that if we want to go green, we have to go digital. The two things cannot be separated. Second thing that is also related to this, EU industry nowadays, depends basically on big clouds, which are from these hyperscalers, which are not European, and moving towards the edge computing is a big push to the concept of open strategic autonomy. Why do we need to go towards edge computing? Rolf already explained many of the technical reasons. I want to tell you one more thing, which is, I don't know if to define it economical or psychological. I used to work in manufacturing before coming to the commission. So I know how a plant manager thinks, a factory manager. If you talk to a factory manager, to a person responsible of the daily work of a big factory, he will be probably, because he's always a man, and you never have a woman in this position, but he will be probably a very conservative person, not because he's stupid or because of political reasons, no, simply because a factory is a huge machine. Every day in the morning, there are, in a big factory, maybe 5,000 employees which clock in, and start working. And if something does not work, you have to pay, in any case, the salary to 5,000 people. So whatever you change, whatever is your dependency in the factory from something outside is something that the factory manager does not like. That's why up to now, for big, heavy computing tasks, you needed to use the cloud infrastructure. Now, edge computers are at the level of capability which makes many things possible, from training neural networks to whatever is needed at the local level. And I'm sure that this is a good reason, there is a good opportunity for this reason to push more towards edge computing in the factory, because the factory is a machine which is has to reduce the attack surface, as Rolf said, not only in terms of cyber security, but in terms of anything that can go wrong. The factory is as much as possible to be an autonomous system with a lot of interfaces with outside, because you have goods and services coming in, goods and services going out, and so on. But having computing platforms which are as much as possible edge oriented is definitely better for a factory. Okay, now I want to show you something about the Horizon Europe work program. As Rolf said, this is not official, but as it was shared with member state, I think that everybody working in research in Europe has got a copy of the drafts. So I think that I'm not saying anything really new. I would like to guide you a little bit in the complexity of Horizon Europe, because Horizon Europe it's not, I was saying it's a mess. It's not a mess. Actually, it has a good structure, but it's very complicated. There are many things. Let's see what is important for manufacturing and for edge computing in manufacturing. Horizon Europe is divided in 3 pillars. The important pillar for us is pillar 2, global challenges and European industrial competitiveness, which has several clusters: health, climate, mobility, and so on. The important cluster is, I think it's cluster 4, digital, industry, and space. So puts together digital and industry, which is quite, an important message in itself. And of course, space, which is maybe less important in terms of volume today, but very important strategically. Then there are the destinations. And if you look at the destinations, there are at least 3 which are very relevant for manufacturing, for edge computing in manufacturing. One is these world-leading data and computing technologies, which also Rolf was mentioning, where there is an effort to create the future European platforms for the edge. So the meta operating systems that will be the software stack at the basis of the edge computing for the future. Then there is AI enhanced robotics, data-driven industrial environment, and these 2 are part of the area which I'm working on directly, is Made in Europe. So Made in Europe is a partnership. What does it mean, a partnership? Partnership means that European Commission works together with an industry association. In this case is EFRA, the industry association of the factory of the future, to define the themes on which research will be financed, and the partners of the industry association commit to investing in this. So presenting proposals and which are financed at 60% or whatever. So they have to put some money in it, because they will do, because they think that is important for them. So this Made in Europe partnership is let's say the place to look at for all the technologies which are relevant for digital technology in manufacturing, in manufacturing of products. While the cloud to edge to IoT is supported by 2, if I'm not mistaken, by 2 partnership, Made in Europe and the other one on AI, data, and robotics. Last but not least, under the destination for digital and emerging technologies for competitiveness and Green Deal, there is a topic which is called edge processor. So is the development of the next generation of chips, of processors, especially for edge application, which have to be low power and high performance, let's say. Basically, is the attempt from Europe, the attempt of Europe to become autonomous in terms of intelligence of chips for computers from other partners outside of the continent, and is very strategic, very important. Now, there is little doubt that in Europe there is the know-how for designing a next generation processor which is better than the ones that we have today, that you know, uses 1/10 of the power and is more adequate for the recent workloads in artificial intelligence and so on. The fact of manufacturing the processor in Europe is a lot more of a challenge, but it's one of the areas where we will I mean, we will see if Europe in the future can really be strategically autonomous and able to develop internally a technology which is strategic for the industry. So that's all from my side. I hope I've not been too long. I just wanted to give you this feeling of Horizon Europe, which is our tool for supporting all the research. While Digital Europe, by the way, is the program that we will use to deploy the technology, to build the capacity. So Horizon Europe is the BioNTech which developed the new vaccine using a brand new technology, and Digital Europe is the thousands of nurses which are shooting the vaccine in the arm of people to make it work in practice. This is the idea that we should have. So Horizon Europe will develop the new technology. Digital Europe will make that technology available across all the industrial sectors. And I hope that this makes this concept a little bit clearer. That's all from my side.
Thank you so much, Sandro. Sorry, needed to find the unmute button. No, this is very good with such a comprehensive overview. I think it's really helpful. So with that, I don't know if there are any questions in the chat. Maybe you're monitoring, Catherine, but we can certainly come back to that before. I mean, after the interventions here. So now we have from the IoT perspective, from the industrial ecosystem perspective, from the policy perspective, as well as the technology roadmap view, what is the baseline? So let's continue and hear from the stakeholders and the community. And we have a very nice lineup in the two sessions here today. So as you know, before we focus first on industrial IoT, and then we dive a little closer into the edge node use cases before taking some visions and statements. So I would like to invite Vivek Kulkarni from Siemens to the floor to present and to give the perspective, I would say, from the receiving end of this landscape overview, and as one that is instrumenting a lot of shop floors, as well as all the other computing continuum elements that we just heard about. So let's see if we can get you shown here. You're okay, Vivek? Do you want to show the slides?
Yeah, I cannot share my screen because
sharing?
I think, yeah, exactly, yeah. So now I can, I guess.
Now you can, and we can see you.
Right, yeah. All right, I think you can also see my screen. All right.
Second.
Yeah.
Need to get the inner workings going. At least I don't see it yet.
You're...
See it.
There it is, full screen and everything. And we hear you. So please.
Okay. Perfect. So thanks a lot, Martin, and thanks, Rolf, for inviting me for this thematic workshop in manufacturing. So I'm Vivek Kulkarni. I'm working with Siemens as senior key expert in Munich in Germany. And the topic of my presentation is industrial IoT and manufacturing use cases from the project Intelliard, which is basically part of the NGIoT, so next generation IoT project, so ICT 56. So let me stop my video just because to share some kind of to stop the bandwidth problem at my home, just for a kind of a home office environment, and also for you as a kind of audio experience. So just I will stop that video from my side. All right, then, over to the agenda. So agenda is as follows. So first I will give a background on industrial IoT, especially the projects which I coordinated and executed in Horizon 2020 projects, along with the considered business drivers, business value drivers. So then in a nutshell, what are Intelliard manufacturing use cases and associated technical challenges, and finally the planned work in the project. So let's start with the reference project in the context of industrial IoT. So it all began in 2015 with the project Virtuend, which belonged to the phase 1 projects of 5G PPP. So there the research question was how to install new sensors into programmable infrastructure in order to provide value-added services to wind park operators. As an important outcome, there, in an operational wind park, operator can control wind turbines over SDN NFV programmable infrastructure and can access new sensors from remote control center. Then over to the Semiotics project, which was basically the IoT project, so just completed by the end of 2020. There, the research question was how to realize the local embedded intelligence in a wind turbine. So the outcome of semiotics, there we demonstrated the local analytics functionality for anomaly detection, especially for using the video anomaly for grease leakage detection into the rotating parts in the turbine, as well as audio anomaly if you would like to avoid any kind of unwanted noise, which basically goes beyond certain decibel level, and also the inclination of the tower. So if the inclination of the tower goes beyond certain threshold value, then in all these 3 cases, the turbine should stop just to avoid any kind of a damage to the rotating part. So now coming to the Intelliard, which is the next generation IoT project. So here we have a research question, how to make use of AI ML at the edge to act on the data locally. Currently, we define 3 use cases, namely manufacturing, agriculture, and healthcare, with feedback from the end user workshops. In all these projects, we have one thing in common, that is industrial IoT. Then, so in all these projects, there are 11 business value drivers, which can be classified in 3 classical categories of time, cost, and quality. So starting with the time domain, so the ease in installing and integrating industrial IoT devices will definitely reduce the time factor. Usability, interoperability of industrial IoT will bring rapid innovations in the market. Cost reduction with predictive maintenance, better asset utilization, remote maintenance, or training via augmented reality. Scalability of industrial IoT systems brings down the cost further. Quality control of the sense data and reproducibility of the results bring trust in the systems for the end users. Data quality of the sense data is very much crucial and critical for AI ML algorithms for their correct and basically the expected behavior. Coming to the reliability in extreme industrial conditions, such as failover scenarios, is an important quality driver, so as security and safety. Now, this brings us to the current ongoing ICT 56 project, that is Intelliard. It has started in last October and will last for 3 years with overall funding of 8 million euros, including 830K euro for 2 open calls. So more information of the on the project, you will get it from the website, especially the cool project video and flyer. So Siemens is coordinator and technical manager of this project, and we have a balanced mix of large enterprises driving NGIoT use cases in manufacturing, agriculture, and healthcare, well-known academic institutions with required expertise for NGIoT technologies are there, along with the innovative SMEs. Now we come to an interesting use case of manufacturing. So it is a human-machine collaboration or cooperation in shared manufacturing setup. So we foresee that in future there will be a shared production facility with highly customized product with small quantity. So this situation is very well applicable to small plant owners to big plant owners sharing their production resources with other departments. So let's go step by step. So in step one, the customer defines the manufacturing goal by sending CAD drawings with material and finishing specifications to the plant edge. Then the process planning and machine orchestration or process happens in step two as per manufacturing needs. In step three, in case there is some problem with the product specification, plant edge contact customer for clarification. If a certain production process is undefined or unclear, then plant operator help with the process planning. So once all the processes are planned in step four, the commands for transportation of the raw material are sent and production data is also sent to the robots and the machinery. In step five, local AI in the robot arm trains its movement to handle that workpiece. In doing that, if the robot arm with camera does not understand how and where to grab the workpiece, then it asks human operator for help in step six. The operator with AR glasses trains the local AI how to pick that workpiece. In doing that, local AI gets retrained in step seven, and the newly trained model update is sent back to the plant edge as step 8, thereby to distribute that model, which is aggregated model, to the other robot arms in the factory. So plant edge is realized on Siemens Industrial Edge. Then we have a robotic arm with TSN joints. So every joint is having a TSN um, uh, 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 let's say it is TSN point, which can be controlled by the network controller. And plant operator is equipped with the AR glasses. And so you can see that this person is wearing the AR glasses here, and he's having this kind of a stylus, which basically I have zoomed here. And with that stylus, basically it can basically operate the robot arm and train it and control it. Okay. Coming to the infrastructure setup in this manufacturing use case, so the customer sends the product specification via public internet. The internal communication between the plant edge, robot arm, and the machinery happens over time-sensitive network, in short, TSN network. The plant operator communicates with plant edge via 5G tactile communication. Additionally, we have AGV communicating with the plant edge as well as the robot arm. So this work is basically not envisioned in the project, but we are looking for this extension to the use case via open call participant. So if you know any innovative SME which can bridge this gap for us, then please ask them to contact us through our website. So for robots and machinery, we have a robot arm with the camera inbuilt, and 2 to 3 automation systems like milling and drilling machines. For the manufacturing use case on the setup, we defined 3 scenarios. So first is collaborative IoT, so where IoT edge devices collaborate amongst each other. Second, human in the loop scenario. Basically trains the robot when it does not know how to grab a workpiece. Third, the trustworthiness scenario via DLT for smart contracts. Let's shortly see these scenarios. So in collaborative IoT scenario, the IoT devices are planned to collaborate with each other. So here is an example. AGV is basically transporting the raw material um, um, to the robot arm, and when it is communicating with the nearest edge device, and when this edge device fails, then this failover to the nearest edge device should happen seamlessly so that the production or the manufacturing job can continue without any problems. The key challenges here are how to optimally place the compute resources, as well as the containerization of the different services, network services, and so on, is also a challenge. And the realization of the multi-agent system, which needs to be deployed in the background of these applications. Then the second scenario is a human in the loop. So where the local AI on the robot arm does not understand how to grab a workpiece, then it asks a human for the help. The local AI basically gets retrained as this plant operator trains the robot arm, and the model update is sent to the plant edge through the edge orchestrator, where the models are merged, and these new models are sent to the other robots in the factory. So this is called as distributed AI, and the key tech challenges here are basically how to define the local AI model in a universal way. Then the interaction between the TSN and 5G network controller in order to facilitate the tactile QoS flows required for the AR, VR glasses and the stylus to control the robot arm, and offloading of the control or the compute capacity from the AR glasses to the edge is also important criteria. Then lastly, the third scenario is trustworthiness, which includes the security, privacy, and trust. So
Vivek,
here,
just to say that we need to wrap up also because of the other speakers. But I mean, please finish this. It's
sure,
very,
this
very
is
good.
this is
Please.
last. This is just last slide.
Fantastic.
Yeah.
Fantastic.
Yeah. So the third scenario is trustworthiness, which includes the security, privacy, and trust. So here we foresee smart contracts via distributed ledger technology in place between different machine vendors, between the plant operator and robot, as well as between customer and the plant itself. The key challenges are how to realize the energy efficient DLT, then its platform interoperability, and finally, even implementation of smart contracts via DLT is a big challenge. So these are the three scenarios we have in the manufacturing use case of Intelliard. And so on our planned work, as I mentioned before, Intelliard started in October 2020, just 2 weeks back. We conducted end user workshop for manufacturing end users. So we got very interesting feedback from them, from machine builders and automation component vendors. So this will enrich our Intelliard framework. And the first version of it will be released by November this year. And we also have the open call, which will enhance the Intelliard use cases further with additional functionalities. So all these functionalities will be showcased in this use case demo. And for the later half of the project, the same cycle repeats. So I think that's basically it from my side. Regarding Intelliard project and its implications on the industrial IoT in manufacturing use case. So thank you very much for listening, and let me know if you have any questions. Thanks a lot.
Thanks a lot, Vivek. No, this was incredibly inspiring and helpful. I think also to see how the big abstract challenges actually map on these very, very concrete innovation parts on the shop floor with the key challenges. So you could almost, reflect them onto the entire society, and it's just the shop floor with these very, very concrete challenges. No, very, very inspiring. Thanks a lot. Now we have Janne from Nokia, and I'm guessing it fits quite nicely with what we just heard here from Intelliard, IoT, and Siemens, because you need some networking capacity also in these use cases. So Janne, please take the floor and give us your perspective on the industrial IoT domain.
Okay, thanks for the nice introduction, and I hope so, and I think so that it will fit nicely to the present.
Able to?
Can you hear me? Are you able to hear me? Hello?
Yes, we hear you perfectly well. Yes, we do.
Okay, sorry. Okay, I will do the same as Vivek. So I will quickly just say hi, put the video on, and then to save some bandwidth, I will switch it back off and then move to my presentation. So let me share my screen. All right, and start the presentation mode. So I'm very happy to have this opportunity to talk today about artificial intelligence for campus communication and how we can utilize AI and ML in the automation of the management of these private campus networks in manufacturing and also otherwise. Why is AI and ML an important topic for the campus networks? So first of all, there are specific challenges in the networks, which come from one hand from the diverse applications and complex applications that are deployed in those networks, having certain requirements also towards the communication infrastructure and also wireless communication infrastructure. So Vivek was actually already highlighting these, like time-sensitive networking and critical machine type communication for IoT. And of course, for edge cloud offloading, for many applications, it's really critical that we have ultra reliable communication in place to enable this offloading to the edge clouds from the devices. On the other hand, in the private campus networks, they need to have high automation levels so that they can be operated without specific network operating experience, or without not a lot of operating experience, so that they can be managed as part of the OT infrastructure easily. And thirdly, in many cases, there are frequent reconfigurations of the production system and the entire infrastructure, and of course then also the wireless connectivity as part of this infrastructure. So it needs to be easy to reconfigure and adapt to these changes. On the enabler side, so as said, AI and machine learning based methods can of course then dynamically or can learn these environments and can also dynamically adapt to changes in those environments. Also, what we can do with machine learning is that we can utilize data from different domains and, for example, correlate data from the production systems and the network management systems, of course, depending on their availability. And the third enabler is then that although the deployments are often relatively complex, they are also in a way more constrained than what you would have in a wide area network, and certain methods are available, like we might have digital models of the environment, so-called digital twins, which can be even utilized in then the network automation of the campus networks. So here I'm actually presenting a very concrete use case, how machine learning can be used in the closed loop automation of private campus networks. This is not now actually strictly manufacturing. So this is a concept we call predictive location aware network automation for radio, or planar for short, which is work that we did in a 5G network slicing testbed at the Hamburg Harbor. And in this testbed, we had 2 cells in the Heinrich Hertz Tower, which were covering the whole harbor area. And we had 3 slices. So we had EMBB, IoT, and URLLC slices for different applications, like controlling traffic lights, AR for the harbor workers. And in this presentation, we will be focusing on the IoT slice, which was used to collect emission sensor measurements mounted on barges or ships moving around the harbor area. We collected a lot of data from the testbed, including base station KPIs, also slice specific, and also measurements from the user devices, like measuring the radio signal strength, some QoS related KPIs, and so on. Also, we had location measurements in the IoT slice from a GPS mounted on the ships. And what we observed in the testbed in the data, we saw that in some parts of the harbor area in the IoT slice, where the ships were of course very mobile, we saw coverage issues due to shadowing from the high embankment of the river Elbe on the northern shore and the buildings, and also simply long distances from the base station. And now, to meet the reliability requirements of the IoT, we could of course provision more resources, add more sites into the deployment, but we wanted to see, could we achieve the same without adding resources with more dynamic network optimization, and especially using machine learning and predictive capabilities of machine learning to do these compensating actions in a way that it will compromise then the performance of the other slices as little as possible. So what we did, we had actually two models. So we first of all had the radio propagation map, learning the radio environment in the harbor area learned based on the UE measurements. And then we had the mobility prediction or mobility pattern prediction model, which was predicting the movement of the barges, of the ships. And this was actually implemented in a bit more sophisticated way using a convolutional neural network, so that we were able to predict also more complicated mobility behavior, like where the ships will turn when they come to an intersection of channels and so on. And with these models, we were actually able to predict up to 90% of those coverage issues, so even radio link failures, up to 40 seconds ahead with an acceptable false positive rate. And now what this then enabled us to do, that we could use those predictions to take some proactive preventive actions in the network. And this was studied in a simulator where we actually created what could be called a digital twin of the whole test bed. So we had a 3D model of the harbor area and actually most of the city of Hamburg. And we were also replicating the test bed in our simulation and, for example, importing real mobility traces of the ships into the simulation so that they were also moving in a realistic way. And with this in the digital twin, we were able to reproduce these coverage issues that we observed in the test bed. So I will not go too deep into technical details. If you're interested, there's a demo on how this works that we presented last year at the IEEE NOMS, and there's a YouTube link where you can find a video recording of this demo. But what I can show here is on the right, you see this chart, which is showing the network throughput and then the radio signal strength measurements. And the dark blue line is the measurement itself. And the light blue line is actually then what our model is predicting for the same key performance indicator 40 seconds ahead. And here this rasterized area shows where we are actually predicting a radio link failure. So you see the throughput drops to 0 and we lose the radio connection. But what our algorithm does, it already reacts based on this predicted radio link failure and reconfigures the 5G network in a way that if you look at the dark blue line, which is then the real measurement coming from the ship itself, it actually does not observe this radio link failure because we have already adapted the configuration of the network so that it can be prevented. So that was in a harbor setup. How would this map to something in manufacturing? So we have at the moment an ongoing project called KIC, which is actually short for the German expression for artificial intelligence for campus communication. This is a German BMBF funded project where we are working together with a number of partners, which you can also see there on the slide. And the scope and the goal of the project is to study how machine learning and AI can be used in private industrial campus network management automation. And here, one of the use cases we are looking into is predictive network quality of service, which is then the use case that we also studied in Hamburg. Of course, there will be some differences. Okay, now we have mobile user devices in the autonomous guided vehicles, the AGVs that Vivek was also talking about, but of course they behave differently than the ships in the harbor. But with some adaptations, we can utilize similar concepts to predict the expected QoS with the wireless connectivity. And these can be, for example, used to optimize the edge cloud offloading decisions, that we can optimize the offloading of computational resources into the edge cloud based on also the expected network connectivity. And if you're interested in more details in the KIC project, I also provided a link here to the project homepage. So with that, actually, I finished my presentation. So I hope I stayed well in time, and then thank you for your attention.
Thanks a lot, Jan. This is really good, and good also to see now how the perspectives complement each other, and in fact, on one hand, how advanced some of the elements are, while still some quite traditional issues remain when the different elements are put together. So it's good to see, and also, I mean, coming back to Sandro's point and Rolf's overview on the programs. So the challenges are at different stages of maturity, right? So there's something where we really need to, go back to the drawing board, and others where it's more about market mobilization and the actors and getting together. We have a few questions, just preparing for the next speaker. Just to be a little responsive to the chat. So first, Oscar, you are welcome to take the floor while we just take a few calls or a few. Let's see here. So from the chat, there was actually to Vivek, and maybe we can link it here as well. So what underlying technology are you using to build that framework that you were showing in the Intelliard? Hello, Oscar. I can stop sharing so you can prepare your slides. So is there, the LF Edge Open Horizon framework, is that something that you look into? Maybe we can have a comment from Nokia as well. The point is that, well, first of all, there are open frameworks, and also are there convergence on the frameworks that are being used in these different exercises, or you're building everything from the scratch? So Vivek, I don't know if you want to go first.
Yeah, so we want to look into that definitely, because we are still at the requirement phase. Yeah, so that means we haven't taken any decision on that framework or the underlying technology and so on. But definitely this is worth looking at. Yeah, so thanks for that hint.
Okay, thanks. And Janne, maybe from your part, I mean, the role of open frameworks, perhaps open standards and so on. I mean, Nokia in general and Bell Labs spending quite some time investing in establishing these commonly agreed standards. So any thoughts on that in more general?
I think you summarized it pretty well. So it's, of course, work ongoing, but we're definitely looking into how we can utilize open platforms and so on to enable this.
Yeah. And then, of course, the next question, maybe we can come back to that in the discussion. Of fragmented ideas where everybody is starting from scratch or building something half. So of course, for those, especially I think also from the Commission side, looking in how can we orchestrate and facilitate the communities around the technologies, as particularly Sandro, so with the ecosystems around the digital industry. So I think we can come back to that. Okay, Oscar, I see you have your slides ready. Please present yourself and add to the perspective that we are now stacking up here on Industrial IoT. Thanks for joining us.
Thank you, Martin, and thank you all the team for having us here speaking today. My name is Oscar Lazaro. I'm Managing Director of Innovali Association, that is an associated research laboratory based in the Basque Country, and we have been working on the area of digital transformation and Industry 4.0 for a number of years. And here today we will share with you a little bit of our vision on how we are building actually some autonomy in the manufacturing domain to motivate the development of this more advanced telecom networking and computing continuum that we are all aiming for with a robust and resilient edge. So trying to bring from this digital transformation perspective, what could be the motivation behind the manufacturing industry to invest and adopt this type of technology. The idea today is that we build from this experience in terms of developing autonomous zero defect manufacturing, and also trying to highlight this message that I think it has already been passed by the Commission, and also now reinforced by Martin, in terms of the importance of integration and alignment in terms of maturity of technologies to ensure that a full business case, not only a technical case, can actually be built for this type of technologies. So I will just move into the slides, just trying to bring some ideas in terms of what could be next in terms of demands from the manufacturing sector, and trying to motivate people to think on the next level of services that have to be supported from the edge, so we can deliver this human-centered, tactile manufacturing intelligence that we refer in the title. From the title, I would like, before I move into the slides, that I will go very fast through them, but I will share the material so people can check the content later on. I would like to highlight 4 elements that are important for the development of AI in the context of Industry 4.0 and increase networking and edge capabilities. The first one is the human centricity of artificial intelligence. Basically moving from the black box approach that we are starting to deploy and experiment into what we called a glass box approach, where human explainability of AI is of paramount importance to provide new forms of control in the factory. Tactile, because the application of intelligence has to be within reach of these smart machines supporting digital infrastructure and federated computing clouds that are the backbone of advanced digital manufacturing platforms. And manufacturing intelligence, because this is at the end of the day what should deliver the value to the manufacturing sector. So if we look at the business drivers for digital transformation, these are well known in Industry 4.0. So basically looking for speed, flexibility, quality, efficiency, security, and new business model. This has been disrupted by COVID, and we can see that actually the application of increased connectivity, remote configuration, operation of manufacturing, automation capabilities are gaining critical value in the operation of Industry 4.0. So there is a disruption and a shift in terms of the values that are driving how the industry and the manufacturing domain will behave in the near future to respond not only to medical crises like COVID, but global outbreaks that are basically disrupting global manufacturing, production, and supply chains. So this sort of shift in values, what are the opportunities that they bring? Basically, they bring the opportunity to accelerate the modernization and digitization of our manufacturing shop floor. We are basically in the transition from smart factories into digital ones, where we see an increasing adoption of the digital twin technology. And really the ambition is to move into an autonomous factory domain, where the operation of the factories become more modular, flexible, connected, distributed, cognitive, and collaborative. And actually is this change in the way we arrange our traditional lines to depart from traditional assembly lines into modular, flexible assembly cells, what are really calling for the type of edge power and 5G or 6G connectivity environments. When we look at what it means in terms of operations of the factory, the application of this autonomy, basically what we see behind is a disruption or an evolution of the interaction between machine, information, and human. And actually what should be supported by the evolution of the continuum between the near edge, the far edge, and our cloud infrastructure is the facilitation of this new machine information and human interaction. These interactions take the form of different types of control loops that will be implemented by an evolution of cyber-physical production systems that are powered by the digital twins. Digital twins that now are not only linked to the engineering process, but they are linked to the product, to the experience, and connected at the process-centric level. So the development of this process lifecycle perspective is actually opening new challenges and opportunities for implementation of basically new ways of decision making. Decision making is not just made by means of just in case information. What we are seeing is an increased integration between IT and OT domain that are basically providing this capability for just in time, just in place information access and processing. With these capabilities, then what we see is an evolution of the artificial intelligence in terms of the digital infrastructures that will allow an evolution in the visibility, analysis, prediction, and prescription capabilities of our systems. And progressively, we will see not only the adoption of a single technology, but a smart integration of different types of digital technologies, 5G, 6G for connectivity, IoT, data analytics, artificial intelligence, and obviously the capability to dynamically adapt and interact. But the digital domain is just one of the two dimensions we have to consider when we see the evolution of the factory shop floor. Actually, what we have to realize is that the evolution of our factories as individual entities or as part of connected and hyper-connected supply and manufacturing chains take two dimensions. One is the digital and data dimension. The second one is actually the automation and collaborative dimension. So we have a physical part and we have a cyber physical part that both define what is the level of autonomy that we have to consider in our factory. This is really crucial to understand what is the type of technologies and type of strategies that call for specific solutions in the edge, in the cloud, and even embedded as part of the smart objects that will collaborate in a manufacturing environment. What we have to understand is that the autonomy level of a manufacturing environment is actually fixed as the cross point, as the intersection between the degree of artificial intelligence that is brought by techniques and technologies like data-driven artificial intelligence, machine learning, but the cross point of this, an intersection of this degree of artificial intelligence with a degree of intelligent automation. Actually, the way in which machines with plug, interact, collaborate in a flexible and modular way will have to complement the capabilities of our digital technologies. And this actually defines different strategies, different speeds in terms of digital transformation that we can observe in different sectors of economy. This results that the application and the development of all this digital infrastructure and advanced network management services should be able to implement not one specific type of control in the factory, but should be able to serve concurrently a combination of different types of control systems and decision support strategies that will combine the participation of humans and machines at different levels of automation. Actually, we differentiate in this approach between 4 different types of control: assisted, supervisory, automated, and collaborative or augmented control, depending on the combination of autonomy and human-centered artificial intelligence that we apply in the different parts of the factory. Why are we looking basically at 0x manufacturing as the driving element for all this discussion? Basically, because at the end, what we aim to provide are enhanced capabilities for our factory, like 0 reconfiguration time, 0 delays, 0 waste, 0 net energy consumptions. These are the driving factors for the incorporation of advanced autonomous processes in the design, production, customization, planning, or manufacturing and logistics, driven by the integration of digital technologies. And when we understand all these complex intertwining and interconnection between the different elements in the factory, then we can actually see what is the flow and of technologies that we have to consider to realize this excellence in autonomous operation. Why is motivated this integration of technologies? It is actually motivated by the need to evolve from today decision support workflow that is basically characterized by increasing levels of latencies from the insight, analysis, decision, and action process from unwanted event detection to what we expect to be a 0x autonomous operation, where we can see that all this process is actually squeezed into a much shorter period of time, and this brings increased value to the operation of the factory that actually calls and justify the development and integration of all these technologies. In terms of this competitive and cost-effective rollout of technologies, what we have to also understand is that the challenge that we face is that this will not happen in just one single go. We will have to work either into a brownfield, so technologies are already in place, or we will have to work even on green fields. So we are starting from new factories. But even in these cases, we have to understand that this process is gradual. This process is evolutionary. So the issue of data integration is actually crucial. In the project quality, we have been looking at which are the implications of this adoption of technologies in the context of manufacturing of a large variety of different products. And what we have realized is that for each of these products, there is a number of technologies and stakeholders that have to join forces and digitally integrate products in order to be able to leverage this sort of artificial intelligence or machine learning-driven advanced production processes. And what is equally important is to understand that for the implementation of these pilots that are basically using artificial intelligence, edge computing, cloud computing, and a variety of digital technologies to realize manufacturing excellence in zero-defect manufacturing, we are actually addressing different phases of the quality control, starting from the quality of the design of the product that we are delivering down to the service itself that is provided on the product itself. This slide basically drives you through all the different technologies that need to be carefully integrated so we can actually realize an autonomous manufacturing process in the manufacturing domain. So networking and industrial 5G play a critical role, but this has to be complemented with a different set of technologies ranging from IoT, fog and edge computing, cloud spaces, analytic platforms, artificial intelligence, or cybersecurity to really deliver a process that can be exploited by industry. So what we need is basically a reference where we can actually use to break the silos, connect our data endpoints, and integrate these digital services. We have done this through the adoption of 3 different types of reference model. The first one to break the silos is to adopt ISO 25447 as the big data reference model for data acquisition, processing, analytics, and visualization. The second element that is actually ensuring that all kinds of data endpoints can be trusted, can be shared in a trusted manner with data sovereignty has actually been implemented with the use of DIN Spec 27070, a standard issue in 2020 that is actually allowing this distributed and federated not only processing of information but implementation of federated learning schemes. And finally, all these big data pipelines that are basically the ground of the development of artificial intelligence in manufacturing can actually produce no value to the final customer if they are not integrated with the platforms and the operation of the overall factory. For this, we have proposed and developed what we call the Manufacturing 4.0 Digital Service Integration Model. That is actually the reference architecture that we use to describe how our data models, our digital infrastructure, and our digital manufacturing platforms and service operations can actually be put together. Why is this important? This is important because with this integrated, if we are able to break the silos, integrate the services, and connect these data endpoints, we can actually deliver the different forms of artificial intelligence that are required to implement the type of control loops that I was mentioning before. And in order to maintain and operate and discuss this type of integrations, let me just very briefly introduce you to an alliance that was set up very recently by 3 companies, our group, Atos, and engineering, to make sure that we have access to a community that is capable to discuss and maintain this type of strategies for digital integration and data-driven transformation. This digital community is actually trying to accelerate the deployment of this type of solutions with a clear message and mission on digital integration and data-driven intelligence. The number of factories that are gradually integrating and the members and hubs that are connecting to this initiative is growing. This is really a very young initiative that was signed by the members in February, but is based on 4 main assets: our flagship initiatives, our body of knowledge, innovation campus, and business network. The flagship initiatives that we are putting together is our network of lighthouse digital factories that, to increase the pilot replicability, have adopted our digital service integration model, our digital integration big data pipelines. So each factory can actually understand how the pilots and the advantages and progress made on artificial intelligence has been made, and assess how far, how close they are for adopting these type of technologies. At the same time, we are building the network of 0x autonomous factories that are actually adopting these pathways for factory automation and creating the necessary ecosystem that is actually delivering this digital excellence. And finally, to increase disruption and resiliency, we are putting together this federation of plug and response manufacturing network. If you are interested, you can follow us, you can participate in our countless events that we basically organize. And after this, I would just basically conclude my presentation, inviting you to follow us, and if interested, also grow with us your business. Thank you, Marta.
Thank you a lot, Oscar. And I don't know if you could follow the chat, but there was a ton of questions.
Okay.
I think
I will check now.
No, but maybe we can just take also while we have the opportunity and while you prepare, John. So
I will just stop sharing.
Yes, so John Soldatas, he can put his presentations on. So from Rolf, there was a question. I don't know, Rolf, if you want to put it yourself, or we just read it here from the chat.
Yeah, thanks, Oscar. Now the chat disappeared. Wait a second.
I can read it for you.
Yeah, thanks for sharing the vision with us. I think that is basically the midterm, long-term vision. You have to deliver under the factors of the future, or the future made in Europe. I would be interested. You were not pretty detailed. You talked a lot about data, but how do you see the role of data acquisition and sensor control in the manufacturing edge in the context of AI and machine learning? I think many of the algorithms have to be developed and validated in the cloud level, but you were not quite precise, where we need more cloud resources, or do we need more edge resources, or what would happen there?
Yeah, I would like to, Rolf, just 2 points on this. The first one is that what we are experiencing and piloting at the moment is relatively static. And let me explain what I mean by static is everything and lots of the things that we do actually happen offline and happen offline precisely because the development of the algorithms are actually, and more than the algorithms, the models that we deploy on the edge are actually driven by also human collaboration. So the process is relatively static at the moment, and at least in the near future, I don't think we will see a big change on this approach. Also, looking at the issue of safety and the issue of having to deal with certification, certification of safety aspects of our automation and machine equipment. So I think in that area, what we have to understand is that every time we make a change in software inside a machine, this has an implication on the labeling and safety aspects of the machines. What we are starting to see in some more regulated sectors like pharma is an in-between approach. If the application of AI has a particular purpose that will not change the behavior of a particular machine, then this type of change and modification is actually allowed. And we are starting to see some drafts and recommendations from FDA in terms of how to adopt AI and automation that combines these two effects. But as soon as we identify that a change in software, either in the machine or in the edge that is actually supporting this equipment, will impact the operation and the safety of the equipment itself, it will have to go through recertification. So on-the-fly certification and approaches like we have seen in the Smart Factory KL, where we try to use the digital twin to recertify a particular machine on the fly, are promising lines, but still I think maybe far from being directly applicable in industry.
But, so thank you for the answer. But maybe related to that question, I think we've seen the digital twin, particularly in the energy generation from GE, and the Predix, which wasn't successful because they didn't get the data and the software was not applied at all. And we've seen similar use cases in Industry 4.0, in order to realize predictive maintenance. But you can have best model, if you cannot get access to the data. And we've seen the difficulties of Siemens with MindSphere, having wonderful data analytics tools and services, but with very, very low adoption rate. So how do you see that changing with AI on ML, or what will happen? What in your opinion?
Okay, now I see where the question was coming from. Now I understand, Rolf. And maybe rather than an opinion, I can share something that was implemented in a different project, not quality, but Boost 4.0. It was completed end of December 2020, and Benteler, a German manufacturer of a tier 1 manufacturer in automotive, they have actually created a federated data space across 3 or 4 factories in their group. Okay, but you have to understand that each of these factories is competing inside the group itself. But they have created their own distributed infrastructure for providing information to train the models that then they customize in each of the factories. Okay, and rather than putting the data of each factory in a central data lake, the solution that they have adopted is a more federated and not yet edge power. Okay, they have still done it in the form of data spaces that are and data platforms that are basically maintained by each of the factories. But for me, really, the next step that they are taking is actually that to break this issue of data IP and control, they are building this federated infrastructure so they could learn from the general model, from all the data set, but then they can customize and deploy this in a local environment. And we have seen also some examples of this coming from pilots that, for instance, Comau has implemented in Italy. So I think maybe what we need is to continue working in that direction, because for AI and machine learning to develop, we need more structures and more success stories like those two that they have been recently reported.
Thanks a lot. I think we need to jump to the next one, but it's good that we get the opportunity to follow up. And thanks for the question, Rolf and others. I think we still have some opportunity. We have 1 hour left and we still have 5 speakers. So let's move on. And for everyone, please be concise, so we also have a little bit of time for the questions around. John, thanks for joining us. Many of you will know John Soldatas and his role in IoT in Europe in general, but also as part of the EU-IoT, which is the coordination support action, which is already started, of course, as John will tell you, but also will pick up the baton when the roadmap has been delivered from NGIoT and continue the work under the larger next generation IoT umbrella. So John, thanks for being with us, and please share your vision with us.
Thank you very much, Martin. So I'll try to be quick, but on the other hand, to continue the discussion from where it stopped previously with comments by Rolf and Oscar. And actually, I'm not going to present a particular project in the EU-IoT, but I'll try to make a very quick compilation of different experiences we had, so that we also answer which is the best model for manufacturing at the edge, cloud, edge combination, and so on. I think Oscar explained already some things about the flexibility and modularity in the production. Also the challenges like the need for certification. So we know why we go to the edge, and why some people say that 80% of the data will end up being on the edge and not on the cloud. So it's latency, low latency use cases, energy efficiency, and other things like data privacy and data protection. We also know, and this is, I think, very interesting background, that if you check all the standard-based industrial architectures, so I have listed here the older open fog reference architecture on the right, but also Industrial Internet Consortium reference architecture. So the implementation view described in this architecture is actually cloud edge computing. And you've got different ways to implement cloud edge computing architecture, and this is not specified in the architecture which option is the best. And I tried to make the taxonomy here. So yes, it makes sense to be on the cloud, because on the cloud you can really have a lot of data points, which is important for ML, artificial intelligence, especially deep learning. Remember, the value proposition of deep learning is that it improves. It doesn't reach a plateau. It improves as you have more data. But of course, cloud is not very good for energy efficiency, right? Or for data privacy. If you go to the edge, you get some improvement on some things and a good balance, because you can still have a lot of points. For example, if you are in a fog computing environment, or local clouds, as edge clusters are called sometimes. And then, of course, you can push this to the far edge, to the devices, and have, for example, embedded machine learning or tiny ML. There you don't have so much data, for example, for training algorithms, but you get the best energy efficiency and very good also real-time opportunities and privacy. Now, if you translate this to some of the most popular manufacturing use cases, like, for example, intelligent asset management or predictive maintenance, as some people focus on this most of the time, or what Oscar was talking before, zero defects manufacturing and quality management. So you've got some benefits in being being on the cloud because you have much better calculation of remaining useful life. But going to the edge, even if you have a less accurate model, you can have faster defect prediction and better speed, and maybe a better speed versus accuracy balance. Whereas if you go to the far edge and place, for example, a microcontroller inside the machine and run AI on the microcontroller, you can have probably the fastest possible anomaly detection or defect detection in the machine. Well, the truth is that when we talk about zero defect manufacturing in digital manufacturing industry 4.0, we are actually implying a combination of predictive, preventive, and reactive strategies so that you can make the defects zero. And this means that in practice, you need to have a combination of these models. Now, some experience from Intrasoft we have built through several projects, a platform which is called Datacrop. It's a classical edge cloud platform. So you can use it to collect data in the edge. And of course, you got some well-defined data model, and you can configure both the data acquisition and the data analytics. So it's a framework for zero programming analytics, at least if you do quite common things, classical things at the cloud edge. And of course, you can have this edge cloud interplay with the data. So you filter data and you retain in the cloud what is important, and in the cloud you can build more detailed model. And actually, we have used this Datacrop platform in various edge cloud industrial use cases. So recall, we train algorithms offline, as Oscar talked about, but we have also tried this platform with online data, and we've tested, some popular models for predictive analytics, deep learning, like RNN, or a more specific version, long short-term memory networks. These are classical for predictive analytics, RUL predictable, RUL predictions, and also we have our homegrown Quarma for industry and quantitative association rules mining approach, which actually produce this so-called explainable, if you want, what Oscar mentioned before, white glass models, which are very important for the industry because the models are produced in form of rules which are explainable. So we have tried running on this also with online data acquisition on the Datacrop platform. And this is, how you can get benefit from classical edge cloud computing in a manufacturing context. Now, I'm going to go back to a project that finished last year, where we participated to present a completely different approach. I think it was mentioned even earlier in one of the presentations of this session, which is the use of distributed ledger technology. Most of you know it as blockchain technology, for decentralized coordination of industrial processes. So why would you want to do this? And I think that there was a question about this. Well, you might want to do this when the there is not necessarily trust across the industrial processes you want to coordinate in manufacturing domain, but in other domains. So when you don't want or you can't rely on a trusted third party to acquire all the interactions and coordinate all the interactions, then the blockchain could be a good approach, and you can use it to write maybe the metadata that you need for the coordination, and then the coordination of industrial processes can be a smart contract that you run as a decentralized application. Actually, we developed in the Far Edge project an architecture on how to do this. So actually, we include a distributed ledger, a ledger tier on top of the classical edge tier, which means that you write on the ledger all the metadata of the edge processes and you can orchestrate them based on a smart contract. And we have actually used this distributed ledger for two flavors of edge processes. So edge automation processes. So these are low overhead automation processes where you care about lightweight, fast interactions and fast coordination. Well, blockchain is not a technology for real-time interactions, but of course here we are not using public blockchains, we're using permission blockchains. We have run benchmarks, and you can get, for example, some thousands of transactions per second if you use Hyperledger Fabric. I'm telling this because I think there was a question about blockchain technology earlier in the chat. The other family of use cases we have used this for is edge analytics, so coordination of different analytics processes. So these are more data-intensive processes, and there blockchain can help you first to ensure the reliability of industrial data, and second, to ensure the reliability of the algorithm that you use to process the data, like the parameters of deep learning neural network, without by writing it in the blockchain, which means that you can leverage the anti-tampering property of the blockchain. You can ensure that they can be much more difficult to be hacked. And we have tested this in two factories, in one white appliances factories, and we use this approach to simulate the optimal placement of products on some bays through a sorter conveyor. So we were running a sorter process which was coordinating the different products in the bays. The products were not homogeneous, so the optimal placement of the products from the sorter to the base was a challenge. But also for more classical edge analytics process, like data acquisition on a wheel alignment station, in order to provide to the worker real-time feedback about the quality and the efficiency of the wheel alignment process. So wrapping up, and this was a blockchain-based approach to edge computing, a decentralized approach that doesn't assume that you've got a master edge cloud that is in charge of the coordination. I think this discussion is not over, so we will see that in the future, especially when we want edge intelligence at the point of action, and you have to contribute, you have to coordinate different administrative entities. You can imagine, for example, fleets of different two different car automotive vendors. So I'm going to the conclusions. So I think there are many ways to implement edge computing in industrial environments. Here I presented some, but of course, some of you might be working on federated machine learning, which can be also good for data acquisition and model calibration. And there are even more ways to implement edge intelligence. I think there is the question that, okay, which is the best approach is not a right question, because actually you have to balance a lot of trade-offs: latency, power efficiency, privacy, decentralization, the level of decentralization you want, security and robustness, and so on. So actually, there is not a best edge computing model, but it's actually what is the best edge computing model for your business requirements, for your functional and non-functional requirements. So maybe we need an edge operating system that should take into account these relevant trade-offs and provide the best deployment configuration that balances all this. Let's not forget that the zero-age and the zero defects manufacturing approach combines multiple reactive, preventive, and predictive interventions in order to lead to manufacturing excellence. And in this context, a more modular approach, a federated approach, like, for example, the one promoted by Gaia X, in my opinion, could add some benefit over the more monolithic thing that we have nowadays, that you need, to jump on a cloud edge infrastructure for a vendor and then be more or less tied to it. So maybe GaiaX will bring some good news in the modularity and flexibility we want to pick up the right edge computing paradigm. And that's all from my side, Martin.
Thanks a lot, John. Very comprehensive, but also really to the point. Very nice overview there of the different network capabilities and characteristics. And thanks you also for mentioning the DLT question that came up. So I think we have a very good coverage now of the landscape. We also spent some time on it, but I think that's fine. Maybe you can stick around, John, for also for the next session. Do you want to go over the edge node use cases, or do you want me to do that, and you are more like a commentator discussing?
Yeah, then you can go on, Martin, and I think if we have time to run a panel, we can. We are short of time also, and understand.
Okay, good. So we do it in this way, because then I think you have very good incision points on this. So let me just thank all the colleagues for presenting this overview. So we are on the previous slide here. Vivek, Janne, Oscar, and you, John, thanks for your contributions. We go now as the new normal without breaks or anything. I hope you can find ways to either fill up your coffee or take the bio breaks you need to the next part of this overview session. But we dive in now to the edge node use cases. And to help us there, we have Carlos, Francesca, Chaba, and Jan. And as I said, we also have some time, but we don't have that much time left. So I ask you please to be very focused on the cases that you bring to the table, and then hopefully we can have some interaction there as well. There's only, I think, one statement to be delivered in the open session after this. So without further ado, Carlos, do you want to present your view here? Can you see us and hear us, and can you take the screen?
Yeah, thank you, Martin, for giving me the floor. 1 second, I'm going to share my screen. And I think, can you see it?
Yes, and we hear you loud and clear. Please,
okay,
please be mindful of the time, because
of course,
it will hurt us.
I will try to be brief, no worries. I will switch off my video just to save bandwidth. Okay, first of all, thank you, Martin and Rolf, for inviting me here and to share my view. I coming the same as my colleague Vivek from an ICT 56 project that is called Assist IoT. And what I'm going with, we have done for this workshop is to make an exercise in order to show the architecture that we have in the project, and additionally to enter in one specific aspect that we are delivering right now, that is prescriptive maintenance for the different use cases that we are having thanks to the edge node architecture. So Assist IoT is, as I have told you, as an ICT 56 project. We have 15 partners in the consortium. I'm not going to enter in this because we don't have too much time. You can see that in the website of the consortium. We have research center, we have big industries, and we have several stakeholders participating in the consortium. So the thing that we are working is we're going to move with the architecture and with an edge node that we are developing in Assist IoT in a specific part of the different use cases and pilots that we are having, from predictive maintenance to prescriptive maintenance. Maintenance is a key part in all the manufacturing process, and it's very important in order to be able to predict different failures via analytics, via artificial intelligence, in order to keep equipment up and running in different parts on different stages of the value chain of manufacturing. Here, when we indicate that we want to move from predictive maintenance to prescriptive maintenance, is that the different aspects that we have in maintenance, that is reachability, quality, safety, logistics of the different components, cascaded damage and interdependence between the different components, supported by the edge, can bring and can enable real-time analytics and actuation, reduce the latency and traffic that we are moving to the cloud and do the intelligence and the decisions close to the things that we have to maintain, reduce the network cost because obviously we will be paying less, to increase security, privacy, and trust, and introduce intelligence close to the event. So edge nodes plus artificial intelligence will bring this step forward regarding prescriptive maintenance. So in order to provide this step forward, we propose the idea behind Assist IoT. In Assist IoT, we try to avoid the traditional centralized architectures and introduce and satisfy the need of the near real-time reaction and automatic decision close to the different events that are happening. That is really interesting and needed for performing maintenance in the different events. So in Assist IoT, we are going to provide this blueprint for a decentralized architecture with the edge node as one of the core components in different stages or different places on all the deployment. Okay, and here we will be introducing smart networking supported by SDN. Also, we will introduce DLT, as we have already been discussed by Oscar, by John, and the questions that we have had in the chat. Smart distributed enablers, we are going to introduce federated learning inside the architecture. We are going to put human-centric tools. You know, the presentation of Oscar has laid the floor also for this, and we will allow with all of this for the different stakeholders to overcome different market barriers. So the central part of Assist IoT will be the new architectural approach. We will address the different needs in 3 pilots that I will present now: logistic, construction, and automotive, and we will be able to provide close to the different events and the places where we have to introduce decision to provide scalability, flexibility regarding data, regarding events, regarding intelligence, and try to be more trustable and provide more efficient environments. So this is the 3 pilots that we will be deploying in the project. In the first of the pilot, we will have in first pilot we will have a decentralized system supported by an edge edge computing with artificial intelligence, in which we will be working with a German SME, Tutronics, that is developing visual artificial intelligence, and also with Ford in order to manage what is the different monitoring of the different failures that a car may have. Also, in the other pilot, in port automation, we will be deploying it in the port of Malta. And in the port of Malta, a part of different aspects more focused on the logistics and the operation of a container yard in the container terminal of Malta, together with a Terminal Link, that is the company operating the terminal. We will be developing different small use cases. One of them will be related with the prescriptive maintenance of the cranes and the different equipment for containing handling. So here we will be trying to be able to learn for the machines, learn for the data that we are gathering in order to be able to provide better maintenance. And less related with manufacturing, but also always a vertical or something horizontal that is appearing in different places. We will have an edge architecture in order to perform work safety in construction sites that obviously can be extended to manufacturing sites. So these are the different enablers, the different components that we will be deploying for prescriptive maintenance. We will have semantic approaches because it's really, really important to have a semantic interoperability between the different data sources that we are having. We will have this human centricity supported also by DLT. We need tactile internet in the environments that we will be working. And here we will be working with 5G and also with TSN, 5G provided by Orange Poland in one of the pilots. So this is the Assist IoT vision, in which we will have a decentralized architecture with hyperconnectivity and interoperability in different components. The one that I think that all of the layers of the architecture that we are having are interesting for us, but we have one of the layers that is called the device edge plane, in which we will be deploying the analytics, the intelligence, the federated learning, and the communication orchestrator in order to handle the different nodes and the different components, the far edge node, the nano edge nodes that we will be having in the deployment. So in this distributed and decentralized intelligence that we will be deploying in Assist IoT, we will have distributed data protection and also differential privacy and different human-machine interfaces in order to handle and to interact with what we are having. So we will have different tiers supported by SDN in the different deployments. And at the end, in the lower part, we will have micro edge nodes, nano edge nodes that will be approaching to the place in which we will be interacting with the environment. Here is very important. One of the comments that John has said in the last slide of the conclusion is the need of a common operating system that can be adapted to the different layers or the different tiers of the edge node. Then the whole maintenance workflow will be performed by the swarm of the different edge nodes communicating and supported when needed by the cloud. So Assist IoT needs, in order to be able to perform all these aspects, what we call the tactile internet. So we will be introducing different, or we have evaluated how the different planes of the architecture of Assist IoT need to be supported by tactile internet. So in the part of the edge plane, we need that the different nodes, the different elements are supported by efficiency in communication, low latency communication networks that can provide support for the data, for the volume and the latency of the data that we have support, replicability, and try to all the time minimize the different latency. Also supported by security, also supported by intelligence close to the different events that we are having. So the challenges of Assist IoT regarding predictive maintenance is that the data is the fuel of the maintenance. So it's a limiting factor. We need data quality and data quantity. And then if we are doing things close to the place where we are gathering the data, the performance would be better. So in order to be able to do this, a key aspect is connectivity and latency. We need connectivity and latency for performing all this activity. And also some interoperability. We need that all the heterogeneous data sources are represented by a common ontology, and these different initiatives are run in this aspect. So the Assist IoT solution for this decentralized architecture will introduce edge architecture, including far edge and nano edge components, federated learning for multi-stakeholder predictive maintenance, semantic interoperability, bringing the result from several previous projects in which we have been involved, low latency communication. We will be using 5G, TSN, and fluid mesh in the pilot in the port in Malta, and DLT in order to be able to track data, contracts, different events, and everything will be supported. And we are performing right now an approach for developing all the components regarding Assist IoT following a DevSecOps approach. So all the information, if you want to gather more information about Assist IoT and the different developments that we are doing, here you have all the information. We will also have, in the same as Intelliard, we will have 2 open calls, and the one will be launched in October this year, and the other one in October 2022. So here, new use cases for the use of the different technologies, including the edge components that we will be developing, could be used here. So that's it. Martin, I hope I have done it on time.
Thank you very much, Carlos. No, it's perfect. And thanks again for being concrete. There's a couple of exchanges in the chat, but I think they relate mostly to the previous discussion. Okay. So let's move quickly while we switch to the next speaker. I'll just so see if I can find here. So Francesca, while you make yourself ready, and please take the screen and so on. So John, if you have any questions to Carlos, picking up the pace now, of course, this is a specific project that was presented, but it has strings to many of the things we saw in the landscaping. Please shoot.
I think, Carlos, the new aspect, right, that you put versus to the previous presentation is that you have to see also the network, right, together. So how the network affects the edge computing implementation, right? Like, you know, the SDN and 4G, 5G, and so on. So this is coming all together, I guess.
Yes, yes. You know, for us, this is really important. You know, we see a clear link between the edge nodes, also with net apps in the core network of 5G, and the different possibility of virtualizing and containerizing components for the edge nodes and moving them and try to link them. So the part of the network is really important right now.
Okay, good. So we move on. Just a small service announcement. Normally these workshops, they run for 3 hours. We had reduced the time a little bit to end at the top of the hour now, but I think we will actually have to use a little bit extra time just to ensure that we round off. But I think it's not too much, so I hope that many of you can stay. Anyway, it will be recorded, of course, and we will see it online. So, Francesca.
Hello, can you see me? Can you hear me?
Yes, we can hear you, we can see you. And the only thing I think needs to be done is to put the slides in presentation mode.
Exactly. Okay, perfect. Then thank you very much for the invitation. I will just switch off the video just to save bandwidth like the other participants, because indeed we are all in home office. And I will put the slide in presentation mode. So, so thank you very much again. My name is Francesca Flamini, and I represent TTTech Industrial Automation AG. And today I would like to give you an example of a real-time predictive maintenance use case in the context of the AI for DI project, where TTTech is participating. So AI for DI is a project, artificial intelligence for digitizing industry. It's part of the Excel joint undertaking, and it's a project that started in May 2019. So we are reaching the end of the second year. So it's I mean, in a good way to its completion. And the objective of this project were basically to develop AI application to be demonstrated in close to real life demonstrator in different industry, to be able to build from the requirement gathered by all these use case and demonstrator roadmaps for artificial intelligence, which could, of course, lead to the deployment in industry of AI technology, and to build a community or complement the already existing community on AI with the knowledge gained in this project, paying particular attention to the ethical aspect of AI, and well, of course, on the application in safety critical applications. So that's as I said, the idea was to gather the requirement from different and diverse industry. So we had different supply chain, 5 supply chain, one related to machinery, one on automotive manufacturing, on semiconductor industry, beverage, and agriculture. We have actually Pommery, the champagne producer, as an end user in that case, and transportation. The focus of TTTech and other partner use case is was in the automotive manufacturing, and in particular was a case of real-time predictive maintenance. The partner, the leading partner of the supply chain is AVL, and then the other partner are listed there. The technology readiness level is not so high because it's a research and innovation action, even if it's of course Excel, so let's say more focus on industrial implementation. And the idea was to use AI method like reinforcement learning, model-based reasoning, based on physical damage models for developing a real-time predictive algorithm for the electric drives, in particular an electric engine and inverters. So we develop a predictive maintenance framework based on data-driven and model-driven approach, and implemented. We demonstrated that and implemented that in a cloud-to-edge framework, where the artificial intelligence at the edge in order to be able to detect the failure in real time and predict the health status of the electric motor. Of course, why that has been mentioned several times. I mean, the possibility to have a real-time response of the application allows to save cost, and in the predictive maintenance, in the maintenance world, where let's say 60% of the cost of a product are related to maintenance, this is something that it's of course very much needed. Yes, this is basically the setup. As you can see, there is the 30 kilowatt 6-phase motors with that is controlled with the 2 3-phase inverters. The control unit in this setup is an high-performance safety microcontrol unit, which is linked through SPI Ethernet connection to an NVIDIA hardware for the machine learning model execution. Of course, in this case, the machine learning model is pre-trained somewhere else in the cloud. In particular, the TTTech proposed this edge cloud platform, where you can see that there is in the cloud or on premises the possibility to manage the nodes, the edge node, and the edge node. At the level of the edge node, we have the virtualization environment, where a sort of virtual machine, main virtual machine based on Xen hypervisor is managing both the virtual network and in this case the container, which are supposed to manage the machine learning algorithm. So the main here is the running continuously and is responsible to send the model, the machine learning model, to the hardware accelerator, because actually the problem that we have encountered is that, of course, the edge device exists, but they are not enough powerful to be able to run a machine learning algorithm. So here we send the model, the inferencing and the data to the hardware accelerator, and then we get back the result in a different container. And in real time, we can also, of course, update the model. So when the cycle is finished at the end of the calculation, then of course the model can be updated to a newest or more performing version. And basically here, I just conclude, this is my last slide, is the architecture of the overall use case, where indeed, so the platform at the edge for use for running the machine learning algorithm is connected to the microcontroller, and the data are both, of course, real data coming from the sensor. And in this case, actually, I didn't mention, but the focus is to get more vibration and sound sensor to be able to, and not, let's say, not electrical data, to be able to proper, let's say, build the model for evaluating the health status of the engine. So both real and simulated data, because of course this is also needed to be able to build a robust model in case of failure, because the failure are not probably so often. So is managed in the cloud, and then when the model is trained, then it's deployed on the edge, and then the results are sent back in a reduced way to the cloud to feed an update. We are also thinking to try to do the learning in the edge and see what are the results. And I mean, this use case, just to conclude, has been based on the use of off-the-shelf, let's say, hardware accelerator. In the other part of the project, there are other partners that also develop ad hoc power control unit and for managing AI application. But in our case, we wanted to focus on what is available at the moment, and also, let's say, at a reasonable cost. And I just conclude. Yes. So if you want to have more information about AI for the eye or about this specific use case, you can contact me. Thank you very much for your attention.
Thanks a lot, Francesca, and thanks for this very concrete case, and also with the added perspective that it's actually off-the-shelf products and elements. So, John, how do you see that in
Francesca, one question here. In one of the first slides, you said you are using also model-based reinforcement learning. And my question was, is this appropriate for the edge? I mean, you know, because it typically takes more time, you know, to build and converge. And then I didn't see that in your last slides. I'm talking about the model-based reinforcement learning. Francesca?
Yes, I'm here. Actually, for the moment, we are using in the edge a model that for, let's say, image recognition, we are still working on the integration of the model provided by the other partner, so of the real model. And actually, yeah, there are some issue in terms of yeah, the format that is used. Yeah, so I cannot reply fully to your question, but yeah, I can come back to you.
No, I understand. So the final solution trains the model in the cloud and deploys deep learning at the edge, right? Via TensorFlow.
Yes, that's the idea. So
and you use NVIDIA for acceleration. No reinforcement learning.
Use NVIDIA and Google TPU, to be honest.
Very good. Thank you.
Okay, but I mean, this is what we wanted. We want some very concrete things on the table, which is, I think this is a benchmark, because I mean, there's so much you can do if you have the whole value chain and you can just do your custom whatever. But I think we need to close the gap between those. I mean, what is there on the market today, off the shelf, just order, or as you use as a service, or you have to do everything. So it's these ecosystems in between that we are really trying to map and project. I think we now get a very good contribution as well here. Saba, you're ready from GTCAT in London. Thanks for joining us, and please, I mean, again, remember the timing, but also we are now in this series of very concrete, well, edge node use cases. We're trying to define what the heck is the edge node, so that not only we can answer to the digital decade when they ask, but also where are we in terms of maturity of ecosystems mapping to the different uses and so on. So thanks for joining us, and please take the floor.
Thank you, Martin. Let me just share the sharing is enabled.
It's a nice office you have.
Thank you. I wish it would be real. Am I sharing already something?
Yes, now we see the full screen, but it's not in presenter mode yet.
Present.
Excellent. We hear you and we see your screen.
Thank you.
Take it away.
Let me actually turn off my screen, my sharing, so that we don't have problems. Am I sharing screen or am I sharing the? Yeah, just.
It's fine. I mean, either way, it's very good.
Okay. So let me just. I have some quick introductory slides. I know there are some pressure in time, so I try to be fast. I'm Csaba Király from representing Digital Catapult here, and I'm glad I can present here. Thank you for the opportunity. Just a word about Digital Catapult for those who don't know. We have this not so simple mission of accelerating the early adoption of advanced digital technologies in the UK. So we are sitting between research, academia, government, different types of industries, SMEs, and actually the Catapult network of similar catapults working on other technologies. We are somehow similar to digital innovation hubs in other European countries, and there are some counterparts in other European countries like us with a slightly different structure. We have different technology teams, and I'm sitting in the IoT team, which you see here: future networks, immersive technologies, artificial intelligence, and distributed systems. So just a few introductory slides on the edge and the hype, which I wanted to put because here we are speaking from, this was left side is from Gartner from 2018, right side is from 2020, was Gartner. And we are speaking of having more data that is created and processed outside of the cloud. But the interesting question is whether we are moving processing from the cloud to the edge. And I think we are not. What we are having is more data which is being created, or I would say actually captured on the edge. And this is very relevant in the manufacturing sector, where the physical signals are already there. Think of just the audio signals that we have next to the machines, which we capture by human ears, which we see the anomalies now. And it's in the foreseeable future, we will capture these, but also the power signatures and many other things with machine, which generates much more data. And looking at this perspective, I have two slides on from cloud to edge, in which I would like to highlight. These are kind of the usual dimensions. We know about the resource scaling, we know about the economic scale, but two important perspectives in which the cloud, the centralized cloud, is good, and that's it's a natural space for big data. There is federated learning. We have lots of techniques to do things distributed, but there is no replacement for having big data concentrated. And in some use cases, that's just needed, and it's it's especially AI training, it's hard to neglect that fact. The other thing is the fantastic IT tooling and abstractions which we have in the cloud era, which developed from different as a services to the whole DevOps tooling. This is still kind of missing in the edge. We don't have these kind of abstractions we start to have, and we don't have this kind of tooling. There are things wrong with the cloud and good with the edge, which point in the direction of the edge. And these are, again, kind of well-known dimensions. I was trying to have a list of these. One is the data which is generated not in the cloud but in the edge, and it's there. Then there is the bandwidth, and this is absolutely important when we are thinking of capturing physical signals. Think of, again, just having power measurements and having more and more refined energy footprints of machines and anomaly detection, for example, based on that. That's not something you want to send to the cloud. Then there is the latency problem and the autonomy problem, which is became very relevant now with COVID and all the remote operations that we have. And then there is privacy, or more importantly, data security. The rule number one, and again, this is very important in the manufacturing sector, is still the same. You don't share, you don't risk. So whatever data you can keep local, you are reducing risk. And then there's the costs related to money and energy spent in communications, if it's communications cost, which is the bulk of the cost. And finally, the legacy operations technology, which is embedded in the field. There is the IT-OT divide, but there is also something which is the operations versus R&D and innovation divide, which I will have something about later. But let's go to the concrete specific example. So we are working in a consortium, which is the DETI, Digital Engineering, Technology and Innovation, funded by the West of England Combined Authority, in which we are working with automated fiber placement machines. So these are very nice manufacturing machines, manufacturing complex composite parts. So I think the prime example of these are airplane wings. And I think it's quite obvious that these are critical and complex in many aspects. So basically how it works is you have tapes which are fed through a delivery system, and these are going to a head, which is a fiber placement head, which is going on a program path, and it's putting layers of fiber one on each other. Actually, it's working on putting it on a work surface, and with this, it's creating something which is called preforms. And then you have these individual layers which are consolidated on the fly, and consolidation means you have pressure roller, which is applying a well-defined pressure, which can be defined in each point, and then you have a heating system, which is applying heat. So it's quite an impressive manufacturing process. I was inclined to put a video, but I didn't want to risk that. And in this context, we have a project in which we have IoT technology applied in different cases. And this really lends itself to applying IoT and Edge technologies. So what are the cases that we are looking at for the AFP machine? The first is predictive maintenance. Predictive, but also preventive, prescriptive could be, but predictive maintenance is the main. And also enabling servitization to optimize, and this is basically optimizing the maintenance operation and the uptime of the machines. And then there is the manufacturing process inspection and the control of the process, which in this case, keeping the manufacturing tolerances is of utmost importance. Materials could change, many things can change, and you should have these kept that way. Then there is product quality inspection. So specific to this manufacturing process, there are different typical problems with manufacturing process. It can be wrinkles, gaps between the fibers, twisting, inclusions, etc. And these quality inspection is something that you can do, for example, monitoring with different techniques, from video-based to lasers. And then there is material and asset tracking. tracking of materials that are going to the production, the location, actually the conditions in which they have been. Materials should be frozen before in a freezer, then they should be get out of the freezer, then these should be fed into the machine, and the temperature and everything should be monitored. And then one which is quite important is the environmental impact monitoring of the manufacturing process. So here we are working on qualifying the carbon footprint of the production process, looking at the AFP machines' energy consumption, but that's still quite. If you just look at it as one number, it's not something complicated. But if you start to look at the actual consumption of the parts of the machine itself, the different subcomponents, and then you start to add up things like the clean room, which is around this, and the building around this, and the materials, and the storage of the materials, and the IT infrastructure, and all else, and the waste. Then you are getting to a quite complex problem. So this would be if you would manufacture using AFP machines, like a big airplane manufacturer. But an important aspect I would like to highlight is that IoT is used also in the R&D process around AFP manufacturing. So here we are working with a company, with a research center, which is the National Composite Center, which is doing research on the manufacturing process itself. And then new questions are brought up, and more IoT infrastructure is needed to answer these questions. So questions like what are the compromises between cost, speed, structural properties of the actual object, manufacturing tolerances, and the carbon footprint of the process? Or what is the actual carbon footprint related to the R&D process itself, going into developing the manufacturing process? And what level of insight we can provide to help these decisions? And there is also another important aspect in this, is the IT-OT divide, or more the OT and R&D divide, I would say, which is, we are speaking of a space in the manufacturing facilities where collaborative research and development has some difficulties. This is well known to be difficult on the shop floor. And this is partly related to the tooling of IT and IoT and OT tooling and the interlinking between those, on which we are working with the gateways, and also the organization aspects. So, and this is not just a problem in the R&D facilities. Actually, and I think it's a very important aspect, where if manufacturers want to be innovative manufacturers, doing innovation in the manufacturing process, and that's quite important for Europe, then this divide should be overcome. So the question is really, what tooling can we provide to help digital manufacturing innovation in Europe, I would say. Europe has great manufacturing legacy, there's huge innovation potential, but we have lots of blockers. And edge compute and actually reliable wireless technologies are key in this, in enabling this. So what is the technology playing field that we are working with? And
just a quick version, because we are now approaching.
Yeah, absolutely. There's two slides. So this one.
Oh,
so one is the is absolutely relevant to Edge, is the low cost and I would say open source based rapid prototyping platforms as IoT gateways, which are capturing the information. And in this, there have been different research projects. I should mention Agile IoT, which we were running. I was in my previous company. And we are using our open source gateways also here in this project. There are now other platforms. But this is quite important. It's also important to have wireless infrastructures. In an environment where pulling a cable costs several thousand euros, if you want to enable experimentation, you should deal with the cable replacement. And we are dealing with 4G small cells in the 5G Encode project, which is simply, which is also in DATI. And we also placed LoRaWAN and LoRa-based network here for capturing information from environmental sensors, for example, and from sensors on the machine. Then we are working on asset tracking, currently with RFID tags, but also looking into other technologies and other projects. And I should mention also the importance of keeping data safe, where we now have a quantum key distribution infrastructure, and we started to work in the direction of using quantum technologies in IoT. And finally, device edge processing, on which I will have a final slide. On device edge, I think it's really key for Europe to get into the large number of edge devices, intelligence devices being deployed in the manufacturing industry. Here we are currently looking at TinyML, which is the ultra-low power machine learning technology for battery-operated devices. And the current work that we are doing on this, we are working on the performance benchmarking of these. And I'm now providing the reference implementation for anomaly detection for these devices. Fortunately, there are European players here, and I hope to see this taking off. So edge devices on the far edge are really key to have these signals captured and analyzed right in the device, and sending still information to the cloud, but analyzed information. Thank you.
Thank you so much, Shaba. And we got a little bit of everything, some overall and some very concrete case, and then some forward-looking stuff. So that's very, very helpful. We have Jan Höller from Ericsson coming up. Jan, I'll be presenting your slides, but please check in. So John, do you have any follow-up for what we saw here? I mean, yes, it was a little bit
I think
all over.
This was the question that was introduced in the very beginning of this presentation. I think it was a question that was actually asked recently in the last month in Hannover Messe and in IoT World, which are, two big events happening, which is, on the one hand, we have this tech push enthusiasm from our side to push the edge, but manufacturing industry is a bit more conservative. Yeah. And, some people even in the Hannover Messe saying, okay, we don't see this, we don't see so many real-time use cases in the factory, maybe this is too fast for us or overly optimistic. So there needs to be a balance. And I think in this presentation, this was discussed in the beginning. I don't know if, Shaba, you have any comment on this, but this was exactly the question that was voiced in Hannover Messe in IoT World earlier, in the month.
Yeah, we definitely see this problem, and I think we should create the frameworks and the place for innovation and experimentation in this sense, so that companies have, and that's partly related to tooling, safer tooling, which integrates safely with the factory floor operations technology, in which the cloud technology is at such simplified, I have to say, the DevOps tooling around that is that you have a safe play. That kind of safe play is definitely not there on the edge and not there in the factory floor. And I don't have an answer how to create that, but I think that's important to have that kind of possibility.
We call it innovation potential, and it will go in the roadmap. So I think it's very good to have these. So shortcomings are opportunities, right? Thank you very much, Shaba. So Jan, are you with us?
Yes, can you hear me?
Yes, but I can also hear some noise. I'm not sure whether that's on my side or on your side.
I don't hear any noise. I don't know if there's some echo if somebody is unmuted.
Catherine, can you decide whether it's...
your sound is not very clear, so I don't know if you...
Yes, I agree. We can hear some disturbance with the audio quality.
So
I'll just try to mute me. I'll take me out of the loop, just checking. So maybe Catherine and John, you can check with John.
So how is this?
There is some, some noise, not echo, some noise.
That I do not understand because I'm in a dead silent room and my computer is dead silent.
Now it's perfect. Now it's perfect.
Okay.
Jan, quickly. Talk.
Yeah, okay. I think you gave me, I was not on the agenda yesterday, but I am today, and you gave me 5 minutes and I have -5 minutes. So let's try to do this as quickly as possible. I'm from Ericsson. I've been doing IoT for 15 years in EU projects as well. I will not talk about 5G, though I'm from Ericsson. My colleagues at research are now focusing on 6G. But I will rather talk about something around IoT. If you're interested in 5G in manufacturing, there's actually an alliance called 5G ACIA. That's the Alliance for Connected Industries and Automation. It's a big consortium now of companies that we were co-founding. So take a look at that. There's a good set of publications coming there. You can take, I have two things basically. One slide is around the use cases that we are working on concretely. And the second thing is around some of the IoT topics that are IoT Edge related capabilities. This is just to flash that we have been working on, pushing 5G into industrial context with a set of partners globally. You can look up many of these references on your own, but you can see many of the automated production, connected mines, and what have you that we have been working on. There's a bunch of publications available on Ericsson here if you want to find out more. Focus has been, of course, 5G, but Edge, Cloud, and IoT is an integral part of all of these kind of activities. What I wanted to talk about, if you go to the next slide, is that we are actually a fairly large manufacturer ourselves. And we have built a 5G-enabled smart factory that is manufacturing 5G. And it's a facility in Louisville in Texas. There's also information available of this online. This is a complete greenfield realization of a factory, and we wanted to make it as future and automated and autonomously operating as possible, including it being as sustainable as possible. So energy, and you can see some solar panels here. And we have been looking at, if you switch to the next slide, we have been looking at a set of, so I'm not going to be concrete about one single use case, but these are use cases that we have deployed in the factory as we speak. We have identified something like 73 use cases. We have 34 on the roadmap, and 12 ones have been deployed. And you can see everything from digital thread, where we are collecting information of how each single, basically what we're producing is base stations for cell towers. So the digital thread is one example use case where we need to pull together everything around the components, the assembly, and the ready-made product, the testing, quality inspection, etc., and creating this kind of digital thread. And that means we need to synchronize data across all of these different activities. The main problem here is more or less data in silos, not so much edge. But another one that is interesting here is energy monitoring and management of energy consumptions, as we want to be really sustainable. And issues that come in play here is when the sun is shining on the factory facility itself, it creates heat in certain places, but it might be cold in other places. And we want to control this and predict this as closely as possible so that we can manage how we distribute energy inside the factory if we want to heat or if we want to cool things. And this is typically an activity that takes place on shop. So it's in the factory. We don't need to pull the data somewhere else to process it. It means that we deploy application for doing this kind of monitoring and management locally. In the previous presentation, it was already mentioned here, environmental monitoring and control, like clean rooms and production processes, soldering stations, where we need to make sure that the environmental conditions for the appropriate process is maintained at all points in time. Like if the air is too dry, we need to humidify it, for instance, and keeping track of particles and things in the air. I can skip digital performance management here. And another thing that is important here is augmented reality and for, to remotely and support people on the floor, so that you can work hands-free. We can provide guided instructions using the kind of HoloLens gadgets, provide 2D images, 3D images, CAD descriptions, icons, instructions, video clips, text, whatever information that is pushed out to factory floor, wherever the worker is. Let's see. I can pick something more here. Another one is I think, automated inventory and supply processes. How do we distribute tools? How do we push material, parts, etc., across the floor? Here it's completely with AGVs, so autonomous guided vehicles. We have autonomous mobile robots that are doing everything. And here it's really something that needs to be coordinated on shop floor in how you control the trajectories and how you plan the trajectories of the different machines. They need to be aware of each other, but they also need to be a real-time planning on the mobility and movement of these vehicles on the shop floor, so that they don't bump into each other. Another example is some activity we have done with other manufacturers that are in the steel industry. One of the problems they had is really how that the robots that move on the floor carrying heavy items create a wear on the floor itself. So the problem that they had was, how can we spread out the movement so that it's not the same trajectory all the time? And this requires, very much real time. It needs to happen on shop floor. And it's even, but still you have these more longer time horizons like the planning. Another one is around tracking and tools and things like that, and how we can create a real-time understanding of the entire environment. So spatial mapping of the processes and monitoring that is a key capability here. So these are a set of real-time, real problems that we are solving in the factory. And you can ask yourself how much of this can be solved on the floor itself and how much needs to be pulled to the cloud. Very much of this doesn't have to be pulled somewhere else, but you need to have processing locally. And one interesting factor here is, of course, that data is not produced for one single purpose. Data is reused across these different use cases simultaneously. So that is a quick set of concrete use cases, but not in details. I have details on each one of them. Might be an opportunity in the future to get back to them. If you flip to the next slide, which will be my last slide, these are some of the concrete IoT edge capabilities that we are working on, and some of them are near-term and really real problems today, and some of them are more like future-looking. So picking out something is, how do we manage devices that will be deployed in the factory floor, and how do we make them secured, and for whom are we securing them? We need to secure connectivity. We need to secure application data. There are different stakeholders involved here. And when and how do we secure it? Well, the first point when you can insert cryptographic material is when you manufacture the application processor that goes into a device that will be deployed. And that means that the entire process from that moment until you decommission let's say a machine from the factory floor 10 or 15 years later, including all the different life cycle phases that happen in between, we're including a number of different stakeholders. We need to automate that entire process. And there is already existing technologies for doing that, but what is needed here is really business innovation, because we want to scale this up. Interoperability is one of the key problems as well. Now I lost my screen. And I just want to point out that we know of the brownfield and the greenfield situation. The semantics part has been mentioned. I think that is very important, but we are not taking the activities that we're doing. We're not taking the approach of defining a single ontology, but rather how can we create a lingua franca that makes us able to translate between different models from different ecosystems, and how to automate and discover that kind of mapping capabilities. Another thing is this kind of virtualization. If we talk about today's practice of containers and Dockers and orchestration, I think for the future, if you look at the sheer scale of data sources globally, we will have to have something that is much more small and lightweight in terms of virtualization. So function as a service and serverless computing, I think, will be very interesting thing that we need to push for future in order to scale. And this is kind of data processing enablement and the pipelining. But I think also that making data ready, as data enters into the system, or that when you capture data, you need to prepare the data at that point in time. You cannot prepare it later on because, as I said, there will be multiple usages of data. And so curating the data is important. The metadata extraction and annotation is very important. And then, of course, that data enrichment, like filtering, aggregation, and complex event processing, these are capabilities that should be embedded into a network platform, as I said, based on this kind of lightweight procedures. I mentioned this kind of spatial mapping. These are activities that we're doing now, where we're doing complete 3D scan of our own factory environments and making that kind of digital representation, the kind of digital twin, because this is needed for keeping track of all the processes that are happening, so that how you navigate, etc. And also the idea of creating this kind of context fabric, that context is available for any consumer with a very high resolution, and that is real-time situational awareness for whatever applications that you have on top. TinyML is also something that we are looking into and have done a number of activities on. And I think that this kind of putting inferencing on microcontrollers for very fast reactions and still being very lightweight, I think that is definitely a future thing. And the last thing I want to mention is the hardware acceleration that was also mentioned, like using TPUs or using GPUs. This is something that we need to push down into the network fabric itself. And this is stuff that we're working on, both these well-known technologies, but also looking into neuromorphic computing, what that can mean when you have that technology that can be embedded, and in particular looking at the spiking neural networks. I end there. So that was a very quick run through of some of the concrete use cases that we are using ourselves and developing ourselves together with partners, and some of the key IoT Edge capabilities. Yeah, there's more stuff because we had talked about the ledgers and smart contracts at cognitive layer. I had some questions around the process engineering side. But I think that will have to happen at a separate event. So I finished there. Thank you very much.
But thanks a lot. But maybe we can have that. Now I have the echo again. Not sure why.
I will mute, then the echo will disappear. The echo is always on, not on the hearing end, but.
Yeah, okay, so it's difficult to have a conversation with one party muted, but fantastic, Jan. So you brought about the biggest use case, as you can imagine, the biggest node on the planet, a big manufacturing plant in Texas. So thanks for that, and also with all the complexities, because I think what's happening, what we are seeing now, and John, I'd like to hear your perspective on this, is that we put these cases together and plant them around the landscape. There are some converging concerns that we have to pick up. So you mentioned the interoperability and understanding cross-sectoral semantics and so on. Yes, so we're working on that with minimal interoperability and so on. And that's the entire world working on that, not just manufacturing. So you have this idea, I think, which is very, very central, that data is not created often with a purpose. So we cannot make this tight coupling around the data streams. And that's probably one of the learnings also for the manufacturing side. It's natural for many other more heterogeneous value networks, but really how to then orchestrate, not just technically, but also the value networks, the stakeholders, the market around it, the regulation, who becomes liable when you use, a data stream. It's so complex, and I think your use case is probably the most complex edge node if it qualifies to that. So I think that's very good. Do you want to give a question to Jan also, John? It's so rich, so we can only single incision point.
My question to Jan, which relates, to his last couple of slides, is today I think we have a very rich content, right? We cover everything from the connectivity, the different edge paradigms, AI, and so on. I think the question, especially if you talk, to smaller factories, not only the biggest ones and the fancy ones, is where do I start, right? So where do I start? Do I have to make my brownfield work by making some legacy compliance? Do I need connectivity? Do I need to focus on the data collection? Because there are two in your last couple of slides, there are too many things to be done. So my question is, what is your suggestion, right, for a manufacturer to start and to scale up the IoT, industrial IoT adoption journey? What is the 2 or 3 things that they have to do first, prior to moving to the more sophisticated functionality and to the scale up? That is my question after seeing your the last part of your presentation.
Yeah. Okay. Thanks for that question. I am not the manufacturer myself, but I can think of one thing that is quite interesting is this is heavy machinery and it's expensive machinery, and brownfield is a reality. The question is return on investment for the equipment that you have in the factory. How can you prolong that? And I think that the kind of retrofitting approach could be one solution. How you could instrument equipment and processes that you already have with even more sensors to get even more data, and through that mine and find correlations. That is how I would start, and then let's say in the brownfield try to start to grow a green patch.
That was a very nice closing sentiment. I think maybe we should stop there, Jan. Thanks a lot, and may I also thank you for serving on the NGIoT strategy board. It's incredibly helpful to have had these conversations throughout the whole process of trying to understand what is a helpful roadmap and how do we mobilize the community around IoT and edge computing. So thanks a lot, Jan.
Thank you.
Okay, so a big hand to this round of panelists, and thank you also, John, for inciting some extra questions here. Now I want to move just quickly to the final part here, which we can do very short. So in this case, as always, when we do these thematic workshops, we invite statements and so on. Then there has been a few from colleagues who came across the event. Some were here today, I think most, if not all. So I would just pause for a minute or a second and ask if there are any comments or visions that should be shared now. Maybe if there is not, but I just pause and please, put in the chat or use your voice if now is the moment you want to share a short statement. It will be short. But otherwise, I would suggest, Jan, that you give your question here. You said you had something that you wanted to to ask. So I think maybe this is the good moment to do this. And then what I do next is I give the floor to Rolf to wrap up here today. Do you want to do that, Jan? You had a question.
Yeah, I had a question that has been burning a little bit. It's related to some work that we are doing ourselves. And when we talk about creating, and if we're talking about value networks and getting collaboration going between different domains, we always talk about data sharing, breaking data silos, etc. And we talk about, let's say, APIs that should expose capabilities in a vertical dimension across the layers. But what I'm wondering is about, if you're looking at complex processes that involve a number of different stakeholders. If you look at manufacturing, it's not just the manufacturing site itself, the factory floor, but you have inbound and outbound logistics. So there's a whole chain of actors that need to collaborate. Yes, data needs to be shared because that is what makes the decisions go right. But the question is, there's a set of different enterprise processes that drive everything. The question is, how do we take these underlying capabilities, the sub-processes, the resources, the insights that we get from the system into an enterprise level, so that we can orchestrate it more from an enterprise business perspective, and to make that driven by the various stakeholders, that rather than doing some kind of programming, can express high-level intents based on their priorities and their KPIs into a system that is cognitive, that can orchestrate processes across these different players. So, and that, for me, that goes, yes, you need to build on APIs. Yes, you need to build upon an understanding the semantics of data and sharing of data. But it needs to go even beyond that, I think, in this complexity that we look at. And I did not see anything around that here, actually. I understand that DLTs and smart contracts, it is a very useful tool. We have been looking at that and using it in some smart logistics cases. It's a tool for setting up contracts and sticking and monitoring contracts. And based on the information and insight you gather, you can do analytics on who is a good citizen in my ecosystem and who is a bad citizen, and you can make mining and for optimizing things. But this kind of process, the entire flow from end to end across stakeholders, I think that is something that is very important, and that is not AI, it's automation of these process flows that I'm after.
It's I think what we call a very, very good question, Jan, and probably not one that we will address fully here, but actually in the previous sessions, so where we had smart cities and communities, which is the complexity to start with, and the Agrifood with its very diverse value networks that are actually modeled quite well, at least to some extent. So I think there's a lot of learning, at least from an overall perspective, between these different domains. So manufacturing, of course, with a specific focus, but from the other complex domains, which aren't necessarily clear verticals. Because as you say, when does data from the production become data for, I don't know, health and for climate or something? So these complexities is probably a property arising with the capabilities that the digital technologies give us, and especially when they come to the edge, because this is where these complexities have to be managed. I mean, the facilities and the value networks, they are also somewhere, right? So there's always regulation, there's always stakeholders that aren't necessarily part of the strict value network. Okay, maybe the wise thing to do here is give you the floor, Rolf, and you can answer to Jan, and you can wrap up the session.
Yeah, first of all, let me thank all the presenters today. It was a very rich session today, and particularly also thanks to Jan to your last comments. I think I could pick up on your last comments, but first of all, I think manufacturing domain is on the one hand very high value industrial sector, because it gives a lot of opportunities for wealth employment. But on the other hand, even after Industry 4.0, still what you see on the shop floor, you see a lot of fragmentation of different standards, interoperability issues, and you're still looking for a driving force for the next level. And IoT and Industry 4.0 have been brought up, you know, to connect OT and IT, but more specifically to make more manufacturing data, process data transparent to the enterprise world, to basically to move data to the cloud. Complex event processing, predictive maintenance. I think many of these applications are anchored still in the cloud. If you talk about the future and there, you know, we have two challenges. On the one hand, to get the data, the different data of different processes out of the silos, to connect different manufacturing islands, what we still have, you know, depending on the vendor you have, depending on the business process, you have world-leading vendors, but still, you know, you're operating into silos, which is it's a very domain-specific challenge. But on the other hand, I think in the future, moving away from the IoT paradigm, putting data to the cloud or making IoT process data transparent to the cloud, it's now time to deliver timely and process data or knowledge on the process data. So meaning the emerging IoT edge will be, as Jan mentioned, will be more of a, how could I call it, a multi-tier ecosystem, where you have this, on the local level, you have to bring the different data together. And that means, you know, you have insight into the quality of the component, the logistics, the delivery of material, the material flow, but also to the worker, you know, where does he come from, what is his expertise, and what is his interaction priorities, what is his preference. You have to be aware of the capabilities of the machine, as well as of the status of the machine, and in order then, you know, that the result then is fed into a larger system. So that needs not only process control, it needs more mobile reactions, so maybe mobile moving of material and assets, mobile robots, very dynamic supply of inventory and goods. It means applications which are initiated on the fly, depending on the needs of the machine or the worker, providing decision support, providing visualization, but also on the other hand, also sort of having local optimization of scheduling, depending on the material flow, depending on material quality, and optimization of enterprise resources. That could be cost functions, that could be time to delivery functions, and that could be customization functions. So meaning you move away from sort of a central optimization of resources and processes and enterprise parameters towards more decentralized MES systems with a lot of local operation, with a lot of local support for the workers, where you have to separate threats and different parameters on a local basis, which means you may separate process from maintenance, quality control, worker support, material flow, and process control. And that is a bit of a new paradigm going more to the local, that you have local independent manufacturing cells, which are an enterprise in itself, where you have put together the Dassaults and the Siemenses and the Schneiders and the ABBs of the world on one small island within a larger manufacturing system. So that is also including the vision of a tactile internet on that level, but I think we are far from that vision. I think you mentioned it today. All of that, as I said, was a very rich process. We need new technologies like AI, like 5G, very mobile connectivity. We need the cloud still, but we don't need always-on connectivity to the cloud, because there's a lot of independence and local autonomy, and there's a new paradigm in order to plan, execute, and at the end also deliver quality and excellence in the future. And that is my conclusion of today. I said it's a very complex domain. It's one of the leading domains. We've seen the vision from Oscar today. Yeah, there's ambitious vision, but the underlying technology, I guess, is not yet there. And I think we have to work on enabling technologies like IoT, like edge computing, like homomorphic computing, process and microelectronics, and we need the optimization in the domain-specific world. So both have to interact. So thanks again, and I pass the floor back to Martin, and thanks to Martin and his team.
Thanks a lot, Rolf. And I just check if there's any comments from the other colleagues from Connect. I let you check also, Rolf. But it's very helpful to have you here and to co-convene the community. So as mentioned before, we will continue and deep dives into energy and healthcare. I'm sure we will discuss many of the same aspects, in fact. But of course, with a different set of use cases, at least somehow. So those, unless you tell me otherwise, Rolf, those are the final remarks. And I just want to thank all the presenters, thank the audience, thank the team for the excellent organizing. Thanks to the co-hosting and organizing organizations and initiatives, and to the Commission. And hopefully see you again on 18th of May and at the many other events that are happening these days, just now before Horizon Europe and the Digital Europe program are being announced. So thanks a lot, and talk soon.